I decided to play the hat game too. I don't have any children that go to the University of Texas. I think it's cool that Mr. Woodard's daughter does go to the University of Miami. I just like the University of Texas. I like their logo. I like their colors, and Austin is a great city. So there's my hat for the day. We'll see if Mr. Woodard has a different one in the next video. All right. Thank you, Mr. Woodard, for giving that good explanation as far as how we get visual stimuli coming into our eyes, what it's going through as far as the ganglion cells and the bipolar cells and the optic nerves, how it makes its way into our brains through the thalamus back to the visual cortex and our occipital lobes. This picture that's on the screen right now is in your book on page 175. There's another picture on page 115 back in chapter 3, and I always like looking at both of those pictures to have kind of a complete view of what Mr. Woodard was talking about in the last video. So again, just want to reiterate, it's not just left eye and right eye. Like Mr. Woodard said, you can cover up one eye and you'll still get information going to both parts of the brain because it's the left field of vision and the right field of vision. And that picture on 115 does a nice job of showing that. All right. As we create color in our brains, and it is our brains that are creating a lot of color, and there's a lot of really good videos about this out there. There's a term called color constancy, and that is that regardless of what kinds of lighting conditions are falling on a particular object, our brains will interpret that object as a particular color. So, for instance, in this video that's linked here, there are two cubes. And the cubes, they look like Rubik's cubes, and so they have all these little different squares of different colors. One of those cubes is in more of a red lighting and background, and the other is in more of a green lighting and background. And two of the squares on those cubes look awfully different as far as the color is concerned. But then you move those cubes together, and you can see that those two squares are actually identical colors. Our brains are deciding what color to interpret those squares as because of the surrounding color. There's also a good video if you YouTube Brain Games Color Constancy, and they have kind of a famous experiment where they take a bowl of fruit and they actually create this image of this bowl of fruit with only gray and red color. However, when we look at it, we know that lemons are supposed to be yellow. So even though there is absolutely no yellow in that picture, our brains will say that's got to be yellow because that's a lemon. And so it adds color to the visual stimuli, even though that color is actually not there. That's color constancy. And that's our brains deciding what color we should see based on the brain's experience. Now, color blindness, of course, is the inability to discriminate between certain colors. So most common is red and green. And let me pop this up here. So this is a very famous one. It's in your books as well. You have an image like this with all the red and orange types of dots. And then in the middle, you should be able to see a number created out of the green dots. If I'm not mistaken, I think Mr. Woodard on this slide found somebody in his class that was colorblind that didn't know that they were colorblind until they saw this slide. Because if you are colorblind or have one of the primary types of colorblindness, you won't see this green number in the circle. Okay? Now, part of the reason or part of the explanation for colorblindness is what's called the Young-Helmholtz trichromatic theory. And that is that, remember Mr. Woodard talked about the cones in our eyes, and cones pick up color, those two C's, right? Cones and color. And the trichromatic, just think tri is 3, chrome, color. There's 3 main types of cones, and those cones are receptive to different colors. So one type is red, or cones that are more they're more sensitive to red light, red wavelengths of light. One that's more receptive to greens, and one's more receptive to blues. And you can see here there's yellowish blues, cyanish green, and blue, or to be more precise. Anyway, those 3 types of cones are receptive to those 3 main colors. And then what happens is our brains take those colors in, and then the brain does the mixing. So that we see this massive vast color spectrum based on the brain's mixing of those colors, kind of like taking paint and mixing paints and creating new colors out of paint. Well, if those cones aren't working quite properly, you might end up with a condition like color blindness. Okay, this is kind of cool. I'm gonna go ahead and try this, even though it's a video. I think this will work just fine. I need you to stare at the screen at that black dot right in the middle of the screen. I'm gonna move my picture down, and I'm gonna do this. You're gonna stare at that thing for about 20 seconds here, okay? So for about 20 seconds, if you could just stare at that dot. Keep staring at the dot. Keep staring at the dot. You gotta stare for a little bit for this to work well. Keep staring at that dot. Now the screen's gonna change, but I just want you to keep staring at that same spot, all right? Okay, did you see anything? Now, I'm not going to do it again. It's fun when we do it more than once, but for the sake of the video, I'm not going to do it again. My guess is if you were staring at that dot, you probably saw a red, white, and blue flag flash on the screen because it's just a blank screen. I'm showing that to you. That's called an after image. And that goes with a theory of vision called the opponent process theory. And that is that bipolar and ganglion cells are getting signals from the three types of cones that we saw with the trichromatic theory, but then they process them at a more complex level. And so when those three sets of colors are involved in processing, you get opposing colors. So you'll get cones that process red and cones that process green, cones that process blue and yellow, and then black and white. And what happens is that these are kind of like sitting side by side. And if one of those cones is working really hard, the other one's kind of resting. So if I'm seeing a lot of really intense red, those green cones are kind of resting. Well, same with the blue and the yellow and the black and the white. Well, what happens is when all of a sudden the color goes away, the other cones kick in real quick. And they give the first one a rest. So if I'm seeing heavy reds and all of a sudden that image goes away, then my reds are going to rest and the greens are going to come up real quick. And that gives us what's an after image. So if I go back here, you'll see here green, black, and yellow. Well, once that flag goes away, and the cones that are responsible for the green, black, and yellow, once they can rest for a minute, their opponents are going to come back and we're going to see red, white, and blue. So there's those two theories actually work together, that there are these three main colors or three main cones that are sensitive, I should say cones that are sensitive to those three main colors. But then within that, there's these opponents. And yellow, of course, is going to be added to that. And black and white is kind of this mixture of colors. It gets obviously very, very complex. But both theories are considered to be valid and correct and working together. Okay, and again, that's what we get with an after image, and an after image is simply going to be that sensation that hangs out for a little while after a stimulus is removed. Okay, let's just do one more because this one's pretty cool as well. Okay, so I'm going to go to the next slide, and I need you to stare right at the dot that's in the middle of the slide. Okay, just keep staring at the dot. This is going to take about 30 seconds or so. Keep staring at that dot. Keep staring at the dot. Oh, this is going to be cool, hopefully. Keep staring, keep staring. See all the different colors? It's kind of crazy. Move your eyes just a little bit and look at the screen. It's actually a black and white picture. Those other colors aren't even existent in that. But because all of those cones get tired out looking at this image, once those colors are wiped off, the other cones pop in and they become active if even for only a few seconds. Okay, I'm going to go ahead and stop there and leave it to Mr. Woodard.